record. So we can, how are you feeling with the information up to theoretical? Like, are you feeling pretty good with simulation methods for difference in proportions?
Yeah, I think so.
Okay, so I'll give just kind of some formula notes for the theory based, and then we can look at that worksheet if that sounds good.
Yeah.
And I guess it's just you and me today. Thanks for letting me answer some project questions. How's your project coming?
We haven't even started our Tableau stuff, so I would say we're behind, but
Okay.
we'll get there.
Yeah, well, just make sure that you, they're going to post some information about some helps with putting the data and stuff in. There's some issues with how the data is set up in Tableau and stuff. So look for that to get posted probably sometime today. So
Okay.
who's your instructor again?
Schmidt.
Okay, yeah, she'll get that posted for sure. All right, so we'll kind of we'll focus on the theory based methods for a difference in proportions. And this is what we were looking at in section 5.3. So to find our standardized statistic, we use a z-test. So we're always looking at statistic minus the null value divided by the standard error of the statistic. And with categorical variables, we have to think a lot about what we're actually measuring with that standard error of the statistic, because sometimes we'll use one equation over another. And this null value for the purposes of our class is always going to be 0, because we're always going to assume that there is no difference. So let's talk about the standard error under the null first. So this is when we're assuming that our proportions are equal. So when we calculate that standard error for the difference in proportions, we're going to use a calculation using a p-hat pooled. And I'm going to talk about what that means in just a second, but it's the overall proportion of successes. So we're going to take p-hat pooled times 1 minus p-hat pooled times 1 over our sample size for group 1 and 1 over our sample size for group 2. So p-hat pooled represents the total number of successes divided by our total sample size, so N1 plus N2. So N1 is the sample size. In group 1, and N2 is the sample size in group 2. Questions on any of that so far?
No.
Okay. Is it okay if I go to another page?
Yeah.
Okay. So then when we calculate our standardized statistic, we're taking our difference in proportions, the statistic, minus the null of 0, and we're dividing by that standard error for the difference. And this is the standard error under the null using p-hat pooled that we just talked about. And this measures the number of standard errors the statistic, which is p-hat 1 minus p-hat 2, is from the null value of 0. We know from past experience that standardized statistics that are farther from 0 than ±2 are going to provide strong evidence against the null. If we look back at our guidelines for the strength of evidence for the standardized statistic, to find the p-value, we'll compare to the standard normal distribution. To find a confidence interval, we look at our statistic plus or minus the margin of error, where we're finding our margin of error using the multiplier times the standard error of the statistic. But now when we calculate that standard error, we're not assuming the null is true. So we're going to use each individual proportion. So we're going to use p hat 1 times 1 minus p hat 2, or sorry, that should be also p hat 1, divided by n1 plus p hat 2 times 1 minus p hat 2 over n2. So this standard error is what we're using to find the margin of error for our confidence interval. Any questions on this so far?
No, thank you.
Okay. So our confidence interval then is p hat 1 minus p hat 2 plus or minus the multiplier times that equation, the p hat 1 times 1 minus p hat 1 over n1 plus p hat 2 times 1 minus p hat 2 over n2. Because these are both theoretical methods, we need to think about our validity conditions. So we must have at least 10 successes and 10 failures in each group. When we interpret the confidence interval, it's similar to interpreting a confidence interval for a single proportion, except for we have one added part. So we want to talk about how confident we are. We're going to include our parameter of interest because we're always confident the parameter is within the confidence interval. We're going to have our calculated interval. And then we also want to include the order of subtraction. Which group has the highest proportion? And that's kind of the new addition when we think about interpreting confidence intervals. Any questions so far?
No.
All right, so let's go over to that worksheet. And I did just get it posted on the Google Drive. I forgot to post it yesterday. All right, are you able to see the worksheet?
Yes.
Yeah. All right, so we're looking at a Pew Research study in April and May of 2013. They asked a random sample of single American adults whether they have ever broken up with someone by digital means, email, text, or online message. Is there evidence of an association between age and whether or not a person has broken up with someone by digital means? what we've learned with two-way tables is the explanatory variable is always going to be our columns, and the response is the rows. So for this study, we're going to look at a parameter of pi1 minus pi2. So our groups, one is going to be age 18 to 29, and 2 is going to be age 30 to 64. So when we're thinking about our parameter of interest, we're just identifying what pi1 is and what pi2 is, and then talking about that difference. So a parameter of interest here would be the difference. And parameters are always about population. So we're going to say the difference in true proportion of American adults who have broken up with someone digitally, comparing age 18 to 29 minus age 30 to 64. So looking at the difference in proportions between those two groups. Any questions on that?
No, thank you.
Okay. Oh, there it is. All right. So if you think about notationally our null and alternative, what do we assume is true in our null about the?
There's no association.
Okay, no association. So notationally, we could say that pi1 is equal to pi2, or we could say pi1 minus pi2 is equal to 0. And again, identifying our subscripts. So 1 is ages 18 to 29, and 2 is ages 30 to 64. What relationship are we testing between the two variables or two groups with our research question?
If there's any association.
So what is that indicating about our direction of our alternative?
It's two-sided.
Right, so we're gonna look at not equal. Okay. So this next question asks to calculate the standard error of the differences in proportions under the null. So that means we're going to be using the equation with the p hat pooled because we're assuming the null is true. So we'll need to find out what that p hat pooled represents for this study. So p hat pooled, we're going to go back up and we're going to take all of the people who have broken up with someone by digital means, so 101 divided by our total sample size of 608. And that's 0.166. And then we need our sample sizes for each of our groups. So we have 245 and then 363. And that calculation works out to 0.031. Any questions on where those values came from?
I don't think so, no.
Okay. Right, in part D, it's asking about those validity conditions. Is it valid to use the theory-based approach for the two proportions for this study? So what do we need to know?
How many successes are in group 1 and group 2?
Right, so we're gonna go back up here and then has broken up with digital means this is a success and this is the failure. So we can see we have 54 successes in the first group and 47, which are both obviously greater than 10. And then we have 191 and 316 failures in each group, which are also greater than 10. So which of those responses would be correct?
B.
B, yep. Next week, we'll talk about the difference in means, and we'll be introducing this idea of our distributions skewed or not strongly skewed and thinking about sample sizes. But here we're just looking for more than 10 successes and 10 failures. All right, so now we're going to calculate our standardized statistics. So we're going to take the difference in proportions minus 0, our null value, and divide by that standard error that we found earlier. So up again, looking at our study here, we can find the two conditional proportions. That p hat 1 would be 54 divided by 245 for my group 1, and then p hat 2 would be 47 divided by 363. You're understanding where those values came from, those two conditional proportions?
Yeah.
Okay. Put that in here. So we've got our 54 divided by 245 minus 47 over 363 minus 0, and dividing by that 0.031 that we found up here in part C. We get 0.091 divided by 0.031. It's 2.94.
And a high standardized statistic tells us what?
That that we have strong evidence against the null. So standardized statistics that are farther from 0 than 2 or plus or minus, well, 2 or negative 2 would be considered large standardized statistics, providing strong evidence against the null. All right, so if we think about an interpretation of this value, remember, if we think about our null distribution, or sorry, our standard normal distribution, that 2.94, that's measuring the distance between the null value and the difference in proportions in measures of standard error. Okay, so the sample difference in proportions of American adults who have broken up with someone digitally oops, for ages 18 to 29 and ages 30 to 64 of 0.091 is 2.94. That's my standardized statistic. Standard errors above, because it's a positive value, the null value of 0. Is that making sense on how we're interpreting that value?
Yes.
Okay. So both based on this large standardized statistic, and then we also give the theory-based p-value, what would our conclusion be? Do we have evidence against the null?
Yes.
Yes, and that would be very strong evidence. Remember that a conclusion is always about the alternative. So we have very strong evidence for the alternative hypothesis. It also says include the scope of inference. So let's think about what we would have here. Do we have random assignment?
I don't think so.
Okay, so our explanatory variable is the ages. And we obviously can't randomly assign people into age groups.
Yeah.
So there's no random assignment. It does say that it's a random sample. So this means that we can generalize back to a larger population. We can generalize it back to all adult Americans, but we can't talk about causation. So I'm going to write a conclusion that's also including that scope of inference. So there is very strong evidence that there is an association between age and whether or not an adult American has broken up with someone digitally. Sorry, it's blinking on and off. Don't know why it does that sometimes. For all, because it's a random sample, American adults in 2013. And sometimes it decides to like freeze up on me and then delete everything. All these fun things that happen when we're trying to teach online. Is that making sense on a conclusion?
Yes.
Okay. All right, so now we're going to create a 99% confidence interval using this multiplier. Just to kind of solidify a couple other points, knowing that we have a p-value of 0.0031, do you think that our confidence interval will contain the value of 0?
No.
Okay, why?
Because if it contains 0, then that means that there's a chance that the null is true.
Right, so we don't have evidence against the null. Good. All right, so here now we're going to look at our difference in proportions, plus or minus the multiplier, times the standard error. But we're going to have to calculate a new standard error because this standard error needs to be based on the two proportions. So we're going to find the standard error using p hat 1 and p hat 2.
So how do we know when to use which?
Okay, so if you're finding a confidence interval, you're going to use the two estimates, p hat 1 and p hat 2. If you're calculating the standardized statistic, we're always assuming the null is true when we're calculating the standardized statistic. So we're going to use the p hat pooled.
Okay.
Okay. All right, so we'll find this value first. Our p hat 1 was 54 divided by 245, so that's 0.22. Divided by 245. It's kind of getting annoying, not blinking on enough. And then 47 divided by 363 is 0.129. So I'm just going to say 0.13. So that standard error is 0.032. It's like Christmas lights. All right, so we're taking the 0.22 minus 0.13, because that's my order of subtraction, plus or minus 2.576, the multiplier, times the 0.032, the standard error. And remember the 2.576 times the standard error, the 0.032, that's our margin of error. And this gives me a confidence interval of 0.009 to 0.373, and it does not include the value of 0. It's a little close to 0, but it's not including 0. Questions on that?
No, thank you.
Okay. So then when we think about interpreting this interval, this is where we have to include those 4 different ideas. We have to talk about how confident we are, which we're 99% confident. We're going to talk about our parameter. We're going to include our interval and then that order of subtraction. So the way I like to think about this interpretation is essentially what we're looking at. See if I can write down here. Is we're looking at the relationship between pi 1 and pi 2. And we're saying, well, it could be anywhere between 0.009 and 0.173. So we're talking, oh, that's weird. It's moving things around for me here. So it's the true proportion of the younger age is this value to this value higher than the true proportion in the older age. So we are 99% confident the true proportion of American adults ages 18 to 29 who have broken up with someone digitally is 0.009 to 0.173 higher, because it's a completely positive interval, than that for American adults. (30 to 64). So including that order of subtraction, that we're seeing that those aged 18 to 29 are more likely to have broken up with someone digitally than those 30 to 64. All right, so we've got some true false statements here. 99% of samples of American adults will create a 99% confidence interval, which contains the true difference in proportion of American adults who have broken up with someone using digital means for ages 18 to 29 minus ages 30 to 64. Does that sound like a true or a false statement?
True.
Yep. This is our interpretation of the confidence level. So we know if we take many samples, that what we'd see is that in the long run, 99% of those samples would give us a confidence interval that contains our parameter. A 90% confidence interval is wider than the 99% confidence interval we created in H. True or false?
False.
Okay. It's narrower, right?
Yeah.
99% would be the widest interval we create. There is a 99% chance the true difference in proportion of American adults who have broken up with someone using digital means for the two age groups is within our confidence interval we created in H.
The only thing that's throwing me off is the word chance.
And we can't use the word chance when we're talking about confidence intervals. So this is a false statement. We can have a 99% confidence that it's within that confidence interval, but we can't, it's not a chance, it's not a probability.
Okay.
Increasing sample size will result in a narrower confidence interval than the one created or calculated in H.
Isn't that true?
Yes, if we increase sample size, that will result in a narrower confidence interval. It'll also give us a larger p-value. Okay. Any questions? That's all of the worksheet.
No, I don't think so, but this is super helpful.
Good, good. If you have any questions on your project later or anything, you can always feel free to send me a message. Or, I mean, Jade probably would be very happy to answer your questions as well. But
All right, thank you so much.